Attention P&T smart minds. Are you ready to delve deep into the intricate world of structural analysis? Join us as we embark on a journey to unravel the secrets of form and function in engineering marvels. Let's dive into the core principles, dissecting the very essence of structural stability and efficiency. Before we go further, please don't forget to subscribe to our channel for more insightful content. Introduction to structural analysis. Structural analysis is the cornerstone of civil engineering, providing the fundamental framework for understanding and designing structures that support and withstand various loads and forces. It is a crucial aspect of ensuring the safety, stability, and durability of buildings, bridges, dams, and other infrastructure. At its core, structural analysis involves the examination of how different components of a structure interact with one another and respond to applied loads such as gravity, wind, earthquakes, and thermal effects. By analyzing the behavior of materials under these loads, engineers can predict how a structure will deform, redistribute stresses, and ultimately perform in real-world conditions. Through advanced mathematical models, computational simulations, and experimental testing, structural analysts evaluate the strength, stiffness, and stability of structural systems. This process enables engineers to optimize designs, identify potential weaknesses, and ensure compliance with safety standards and regulations. In essence, structural analysis serves as the blueprint for creating resilient and efficient structures that enhance the built environment and contribute to the safety and well-being of society. Loading. The analysis of a structure begins with the evaluation of the structure's weight and the loads to be supported. Such loads vary both in magnitude and position. The dead load is the load due to the weight of the structure itself. Note that the concrete specific weight is 24 kilonewtons per meter cubic. Also note that the unit is force divided by the volume of the beam or slab. Imposed or live load. This represents the load of other materials, which may be transient or movable loads. Now let's use beams and support as our case study. Note that supports could be columns or walls. Beams are placed mostly horizontally as shown below. The beam section could be rectangular or square. Columns are vertical in nature or diagonal. Columns could be rectangular or square in nature. Load is that force that acts on a beam or a column. Distributed load. A distributed load is the load that acts equally on the beam. It is usually the weight of the beam itself. It is also expressed as shown in the diagram. The unit is usually in kilonewton meter. This is force multiplied by the distance. L represents the length or distance between the support. This is a point load. It is called a point load because it acts at a point. The unit is in kilonewton. In equilibrium, the sum of the clockwise moments about any point must be equal to the sum of the counterclockwise moments about the same point. This principle is often used in analyzing situations involving objects in rotational equilibrium. The statement, total upward force is equal to total downward force, is an expression of Newton's third law of motion, which states that for every action, there is an equal and opposite reaction. This law applies not only to horizontal forces, but also to vertical forces. Beam analysis. The beam analysis is of two forms. 1. Simply supported beam. 2. Continuous beam. Also note that a beam built in at one end and simple in the other is a cantilever beam, also called a continuous beam. Let's see how it looks. Now, simply supported beam is supported on both sides. It is easy to calculate. While a continuous beam has more than two supports, it could be a cantilever. It is not easy to calculate. It requires special formulas or software. Let's solve some simple examples, using the information stated above to solve this equation. Also, considering the moment of the structure. Now, moment is the force times the perpendicular distance. To determine the reaction at B, take a moment about reaction A. Let's make the clockwise moment positive and the anti-clockwise moment negative. Please note that to determine reaction B, take a moment about reaction A, as stated before. This is the force multiplied by the distance moved in one direction, which is equal to the force multiplied by the distance moved in the other direction. Note that total upwards force is equal to the total downwards forces. We can analyze the behavior of each part individually and then combine them to understand how the whole system performs. This technique allows us to simulate real-world scenarios with incredible accuracy. Next, let's explore buckling analysis. Sometimes structures can fail, not because of the loads they are subjected to, but because they buckle under their own weight. By understanding the critical load at which buckling occurs, we can design more robust and efficient structures. Third on our list is dynamic analysis. Structures are constantly subjected to dynamic forces like wind and earthquakes. By simulating these dynamic loads, we can ensure that our structures are safe and stable, even in the most extreme conditions. And finally, let's discuss nonlinear analysis. In many real-world cases, the behavior of a structure is not linear. By taking into account factors like material nonlinearity and large deformations, we can accurately predict how our structures will perform under varying conditions. By mastering these advanced unraveling techniques in structural analysis, you will be able to tackle even the most complex engineering challenges with confidence. Thanks for watching, and don't forget to subscribe to our channel for more insightful content.